Oh, that's way too loud. Okay. How's this volume level? Too loud? Too soft? You can hear me? Okay. Okay. Let's get started then. All right. Let's learn a little bit more about kernels and then go enjoy our Fridays. All right, so what are we doing today? Well, you remember last time on Wednesday, we introduced this concept of kernelization, right? Which basically is a smarter way to allow us to use featureizations of our inputs, phi of x, rather than working with x directly. And we saw how to kernelize our first model, the soft margin SVM. And in order to kernelize a model, what we needed was that we only required inner products, right, between our data points, rather than requiring the data points themselves. And as long as we could do that, we could kernelize it. So we're going to extend that idea today and see a couple more examples of models that we can kernelize. So we're going to see how we can do kernelized perceptron and also kernel ridge regression. And I think that it's important to keep in mind what this allows us to do, right? So at the heart of kernelization, what we're trying to do is featureization, right? Use some features phi of x that are not just x itself, right? And potentially that phi of x could be really large, right? It could have like a really large polynomial featureization, or maybe even infinite dimensional. It's some implicit feature space that I wouldn't even be able to write out, but I can use with the kernel trick. So basically what that's letting us do is it's letting us extend these linear models that we've learned, right? Every single model that we've learned has been linear, right? Linear classification or linear regression. And linear is not exactly a super powerful model, but when we combine these ideas with nonlinear featureizations, right, then we start to get something that might actually be pretty useful when we're trying to handle real-world applications. And so the kernelization idea, the kernel trick, is really one of the key ideas that allows us to extend these linear models that we've learned so far, which are nice and tractable and easy to learn, into problems requiring nonlinear solutions, which is basically all problems that you could probably think of. Okay. So that's kind of the high-level idea that everybody should keep in mind. And I think it's also worth noting that there are a number of models that we haven't learned yet that we're going to study later in the course that can also be kernelized. As it turns out, tons and tons of different models can be kernelized, which is why this is such a great idea. And we won't necessarily talk about all of them as we get there, but it's good to know that a lot of things can be kernelized, so it really is a very general and useful technique. Okay, but let's get back into what we were talking about last time. So remember, what is kernelization? So when I kernelize a model, right, basically what I'm doing is I'm replacing all of these dot products, right, x transpose x prime, with a dot product or an inner product in a different feature space, right? Phi of x transpose phi of x prime. That's the key idea behind what I'm doing, right? As long as my model during training and during prediction only requires these dot products, then I'm able to kernelize it and implicitly use some other feature space phi of x rather than using x itself. So all machine learning models, right, they have to specify two things. The first thing is, how are they learned at training time? What's the training procedure, right? What's the optimization problem? What's the algorithm, et cetera? And then also, once that training is done, how is the model actually used, right? What's the rule or the prediction that it's going to make when it's given a new data point? So those are the two things that need to be specified by all machine learning models. And as long as both of these things can be specified using only inner products, then we're in business, right? That's the basic idea, right? If everywhere during training and prediction we only see these x transpose x's, right, then we're all good and kernelization can proceed. So that's what we're trying to do when we're trying to learn about, or we're trying to figure out how to kernelize new models. We're going to figure out, can we write everything as these dot products? And if we can, then we're all good. And remember, we defined a couple of things, right, like the kernel function, k, right? K is the function that actually computes these inner products in this implicit feature space without needing to compute the featureizations phi of x themselves, right? So that's the key point, right? We never actually compute or store phi of x. We just use this kernel function k to compute that inner product for us. And we saw some examples, for example, the quadratic kernel, right, which can be computed using the original x's, and we never actually have to construct the phi of x that corresponds to those quadratic features, which is nice, right? We save time and we save space that way. And then another thing that's very convenient during training is to have what we call the kernel matrix K, right? Which is basically, you can think of it as like a pre-computing step. Before you start training, you just compute all of these kernel values on all of the xi, xj pairs in your training data. Okay, so these are kind of the two big objects that we're working with, the kernel function and the kernel matrix. So that's what we're doing today, right? We're going to try and figure out, let's look back on some of our previous models that we've learned. Can we figure out how to write them using only dot products? Okay, and then after we do that, swap in this kernel matrix and swap in this kernel function, and we're going to be able to kernelize the methods that we've learned before. Yeah. So the kernel matrix, right? So it's computing, phi of xi transpose phi of xj for all of your xi, xj in the training set. Yeah, but without actually computing phi of x itself. So let's get started. Let's actually look at the perceptron, if you remember this. So remember, the perceptron was one of these algorithms actually that we studied for learning a linear decision boundary between two different classes, right? Class -1 and class 1, learning some w such that w transpose x equals 0 is the line that separates those two classes. This was one of the examples of how we might actually be able to learn this decision boundary. And if you'll remember, the perceptron is actually an extremely simple algorithm. It's basically, in its simplest form, repeating the following update to your parameters theta. Okay, you pick some data point from your training set, xi, yi. Doesn't exactly matter how you pick it. It could be random. You could be going in order. Doesn't really matter. And then you evaluate your current model's prediction on that data point, okay, which is sine of theta transpose xi. That's how we're making predictions, right? If the model is correct, don't do anything, okay? So if the sine matches the yi, which is either 1 or -1, remember, then just move on, don't do anything. Otherwise, if your model got it wrong, then you add yi, xi to the parameters. And then we actually just repeat this process, this very simple loop, until the model correctly classifies all of our data points xi, yi. And this is a non-obvious statement, and I didn't actually prove it, but I want you to believe me when I say that if the data is linearly separable, okay, if we actually have, two classes that can be separated by a line, then this is actually guaranteed to eventually happen, okay? We will eventually have our model, if our parameters are updated in this way, we will eventually have the case where our parameters are correctly classifying all of our training points. However, we also said that if the data are not linearly separable, right, so if there's some mixing going on or some noise, some outliers such that there's no line that separates our data, then this algorithm actually never terminates, because it's always going to be able to find some data point that it's getting wrong, and it's always going to be trying to update the theta, but it'll never get to the point where it can get everything right, okay? So for this reason, perceptron is not exactly a great algorithm, right? It's only applicable in the case where we can actually have linear separability. And like we said before, it's not usually the case that you actually have linear separability, right? In real-world data, things get messy. Maybe you have nonlinear relationships. It's not going to be a good bet to try to throw the perceptron at a problem without being really sure that everything's linearly separable, right? However, there is one thing that we can do to at least partially fix this problem, and that's kernelization, okay? So we're going to kernelize the perceptron. What that's going to let us do is it's going to operate in some higher dimensional feature space where maybe things in that feature space are linearly separable. And if we get there, then maybe we're actually able to learn a linear decision boundary in a higher level feature space, which corresponds to a non-linear decision boundary in your original space, right? Which will allow us to, actually have an algorithm that terminates even for not necessarily linearly separable data. Okay, so that's what we're trying to do here. And as it turns out, kernelizing this algorithm and the linear model are both pretty straightforward. It's not particularly complicated, and so we'll walk through it step by step. But remember, the high-level idea of what we want to do is we want to transform this whole thing into something that only requires inner products, right? I see a couple of problems here with the way that we've written it currently, right? Like we have x's by themselves, right? So if I replace those x's with 5x's, then I'm stuck trying to actually evaluate the 5x directly, which is not what I wanted to do, especially if I have a really high-dimensional 5x, right? So somehow I have to take this algorithm that I've specified and change it into a form that only relies on inner products, and then kernelization can proceed. So that's what we're trying to do here, okay? How are we going to do that? Well, there's actually a very key observation that we can make that's going to make kernelizing the perceptron very easy. And this is the key observation. So we can initialize our parameters to be whatever we want. Okay, it doesn't really matter for the purposes of this algorithm. So let's just, for convenience, initialize them from 0. Okay, so the parameters at first is the entire 0 vector. Well, at every step, right, the update is either don't change theta or update theta according to yixi, right? It's adding yixi to the parameters, right? So if that's the only thing that I'm ever doing to theta, and I start theta as 0, then what's going to be the case is that at any iteration during learning, I can always write theta as this particular form, sum of alpha I yixi for the appropriately chosen alpha I. Okay, if I start theta as 0 and I'm only ever updating it as plus yixi, then I'm always going to have this particular form for theta as long as I know what the alpha i's are. Can anyone tell me what the alpha i's are? Yeah. So the alpha i's you claim should be negative ones and positive ones. Right, so there is a y already in there, so I don't think we have to worry about negatives, right, because we're only ever adding, right? Yes? 0 or 1. Okay, so now we're starting to get somewhere, okay? So if the alpha i's are 0 or 1, kind of what that would mean, right, is that for every single data point, I either added it once to my parameters or I didn't add it, right? But what if I've gone through my data like 2 or 3 times, and there are some data points that I've gotten wrong every single time? Yeah. So in that case, what would end up happening, right, is that what the perceptron algorithm does is it adds yixi every time that particular data point is wrong, right? So I can be adding yixi more than once, right? If I've gotten it wrong twice so far, then I'll have added yixi twice to my theta. Yeah. Yeah, exactly. So the general answer, right, is that alpha I will be however many times the ith data point has been misclassified up to the current training iteration, right? So if I've gone through my data set like 10 times, right, and there's some particular data point that I've just gotten wrong every single time, right, then I'll have added that yixi 10 times to my theta, so then that alpha I would be 10, right? So I can write theta as this sum of alpha I yixi, right, where alpha I is however many times that data point has been misclassified. And if the algorithm terminates, okay, if I actually end up finding some parameters, which I'll call theta star here, because that's what the algorithm returns. If I find some theta star that actually separates my data, then I'll have theta star equal to, again, this sum, right? And I'll define those alpha I to be the alpha I star. That's kind of like, what ends up being returned from my algorithm, okay? I hope this looks pretty familiar to some of you, this sum of alpha I yixi. Hopefully you remember that you saw something that looked almost exactly like this, right? When we were learning about the soft margin SVM and the dual formulation. this is actually no accident. The reason that these things look so similar is because there's a very general theorem called the representer theorem that basically states that for all linear classifiers, I can write it in this way, this form of sum of alpha I, y, I, x, I. The theorem is actually more complicated than this, so we're not actually going to talk about it in this class, but it is kind of interesting that, similar things pop out of all these different algorithms that we have. SVM and perceptron, they're very different, but their goal is kind of similar, and as it turns out, they can be written in similar ways. The solutions can be written in similar ways as well. Okay, so now, essentially what we've done is we've done actually something very similar to what we did when we turned the primal SVM into the dual SVM, right? What happened when we turned the primal into the dual? Well, in the primal, we were working with W, right? Here, that's theta, same thing, right? And then we turned it into a dual problem where we were working with alphas instead, right? There was one alpha per data point, and we were just trying to find the optimal alphas. And then from that, we could recover what the weight vector W was, right? Well, here we actually have a very similar story, right? We were working with theta, but then we figured out, actually, I can write theta in terms of these alphas, right? As long as I have xi, yi, as long as I find the alpha I can then read off what my theta is, right? Just by, multiplying all the things together and then summing them, right? So in that way, I can turn my perceptron algorithm into learning theta, or from learning theta into learning alpha instead. It's basically the same thing, right? It's very similar to this primal dual thing that we've already been talking about. And so that's what the kernel perceptron is going to do, and then that's how we're going to change our algorithm in order to actually make it amenable to kernelization, okay? So let me put two things side by side. The first is the original the original perceptron algorithm, and then the second side is going to be this modified perceptron algorithm that works in the space of alpha instead, okay? So before, what we were doing was initializing our theta. And we initialized it to 0 because it doesn't matter, and 0 is very convenient, okay? Now, instead, what we're going to do is forget about theta. Let's initialize alpha, which is an n-dimensional vector, right? One number for each data point. Initialize that to 0. Okay, that's actually important. Okay, we can't just initialize alpha to anything. It has to be 0. Why does it have to be 0? Yes. Yeah, because at that point, you haven't misclassified any training points, right? And the alpha I is a representation of how many times you've misclassified a training point, right? So it makes sense to keep that at 0. Before, what we did was we now, pick some data point. We're going to do the same thing here, right? Nothing different about that. And then before, what we said was, if on that data point I misclassified, that particular data point according to my current parameters, right? Well, there's a little bit of a problem here because that step requires theta, right? And here, I don't have directly a theta that I'm working with, but it shouldn't be a problem, right? Because I know that theta is what? 0 at the beginning, right? But it doesn't necessarily have to be 0 sometime in the middle of training. So I should have put a loop, actually, on the outside. But in general, theta is some expression that we already know. What is that expression? Exactly, right? I just throw in that expression that I already found, right? I'm using j as the sum now, but that's just a letter, doesn't matter, right? The sum over alpha j, yj, xj, that's my w, that's my theta, right? I can take that whole thing and then transpose it and then essentially multiply xi, right? That's the same thing as theta transpose xi, right? So in this way, I'm sort of implicitly representing what theta is, right? I don't actually have to keep around my theta. As long as I have my alphas and my training data, then I know what the theta is. And then before, what I did was that if my model got something wrong, then I would add yixi to theta, right? Now, if my model gets something wrong, what should I do? Change the alpha by what? Yeah, exactly. So I'm going to add 1 to that alpha I if that data point was wrong, right? So now I have essentially a learning procedure in alpha, right? Every time I get xi, yi wrong, I'm adding 1 to alpha I. Once all my points are correctly classified, I return theta star. On the other side, if all my points are correctly classified, then I return alpha star. essentially however many times each data point was wrong. And then when I want theta star, I can do sum of alpha star y x, right? That's how I'm going to recover theta star. So that's my new perceptron algorithm, okay? You can almost think of it as like a dual problem, right? Now, instead of working in the space of theta, I'm going to be working in the space of alpha instead. But they're equivalent, because as soon as I find alpha, I know how to get my theta, which is the thing that I really want. Yes? So you don't see the kernelization going on yet. That's true. There's no kernelization going on yet. I missed the second part of the question. So the left and right are currently equivalent. Exactly. Yes. So actually, I was about to ask, why are we doing all of this, right? We actually haven't done anything super interesting yet. The reason that we're doing all of this is because, remember, what we want to do is kernelize things, right? And what did we need to do in order to make the kernelization happen? We needed to get rid of all of the instances of x by itself, right? We can only have x transpose x anywhere, right? We're not allowed to have x's by themselves, because what that would mean is that when I want to do featureization, I need 5x. And now when I need 5x, the whole thing can fall apart if that 5x is really large, right? And what I needed was to only have inner products, right, x transpose x, in order to be able to use kernelization and then implicitly compute those inner products using my kernel function. So I claim that we've actually done that, right? So we got rid of all the x's, and now the only thing that I see is this xj transpose xi, right? That's this dot product that I have here, and it's going to be pretty simple to sort of replace that with whatever we want. So we're actually going to kernelize the perceptron now. We're also going to talk about how do you predict using the kernel perceptron. So remember previously when we had a new x, like a test time, and we're trying to make a prediction, what we would do is we would just look at the sign, right, of theta star transpose x, right? Theta star is whatever the algorithm returned to us, right? Well, now we have alpha stars, but that's just as good, right? Because as long as we keep around all of our training data, we can just compute the sign of this sum, right? Alpha star I, y I, xi transpose x. Notice again, right, I have this dot product and only this dot product, right? Xi transpose x, right? So we're really in business now because we really only have these dot products that we have to worry about. We only have inner products everywhere. So basically, if I want to stop working in my original feature space x and I want to work in some other feature space 5x instead, as long as I can define a kernel function that represents that feature space, all I then have to do is replace all of my xi transpose xj, which was, the training points, right, with my kernel matrix, kij, right, the ijth entry in my kernel matrix. And whenever I have to predict on a new point, xi transpose x, I just replace that with my kernel function, okay, k of xi and x. And then as long as I define that kernel matrix and that kernel function appropriately such that it corresponds to the featureization that I want, then I'm all done. Right now, because I've written my perceptron in this new way, learning alpha instead of theta, I'm able to kernelize the whole thing. And that's nice, right? I'm learning a linear model, but now I can work with, more expressive nonlinear feature representations. Let me add a note about kernelizing linear classifiers in general. So we've seen two now, actually, right? We saw the soft margin SVM, and now we also saw the perceptron, right? And like I already mentioned, this idea of doing sum of alpha star I, y I, xi transpose x, and then looking at the sign of that, that looks really similar to how the kernel SVM turned out, right? Like this representation of my weight vector w or theta, right? It's looking extremely similar regardless of kind of which algorithm that I use, the SVM versus the perceptron, right? And in fact, we don't have time to show this, but it turns out that this is pretty much also going to be the same if I kernelize logistic regression, which is sort of, that other method that we learned for learning a linear model for classification, right? So it's really no coincidence that all of these things end up looking the same, at least, from the perspective of all these symbols that we're using, right? It is a direct consequence of what we call the representer theorem applied to linear models. And again, the representer theorem is a little bit involved, so we're not going to cover it in any amount of detail, but it is kind of cool to know about if you want to go learn about it on your own. So then if we take this perspective, right, these solutions all kind of look pretty similar, at least at a high level, right? Really what the big difference is between these methods is that they produce different alpha stars, right? They all produce this form of theta, right, that can be written in this way, but all of the alpha stars that we learn are going to be different, okay? So what was it for the perceptron? The perceptron, the alpha stars, is a count, right? It's some integer that represents how many times that ith data point was misclassified, okay? What that means in particular is that we're probably going to have, 1, 2, 3, 4, like some small numbers, some small, positive numbers, integers, right, for most of our data points, and maybe some data points were harder, and they have, higher counts, but they're all going to be counts, right? This is pretty fundamentally different from the alphas that we learned from the SVM, right? What were the alphas there? Let me rephrase the question. What are the alpha I stars for most of your data points in the soft margin SVM? Usually. 0, right? Because they're only non-zero for your support vectors, for the data points that actually lie on your margin or violate the margin in the case of the soft margin SVM, right? So SVM from this perspective actually is quite nice because most of your alpha I stars are going to be 0. What does that mean? It means that when I'm doing this sum over all of my data points, I actually don't have to consider most of my data points, right? Because that just zeroes out anyway. I only have to consider the data points where alpha I star is greater than 0. As opposed to something like the perceptron, where basically all of the alpha I stars are non-zero, right? And then from that perspective, it gets a little hairy because now I have a lot more things that I need to sum over, and I have a large data set, and this could be pretty cumbersome, right? So long story short, we have something that looks pretty similar in both cases, but that doesn't mean that practically they're going to be the same. Soft margin SVM definitely still has its advantages over something a lot simpler, but a little bit less optimal, like the perceptron. Yeah. Great question. So the perceptron, right, can give you any linear decision boundary as long as it separates the data, right? So it doesn't have to be some notion of optimality like maximized margin like we saw before, right? It could be something that lies really close to some of the data points. Perceptron might still terminate there, right? And that is an issue, and it is related to a number of different factors, the biggest one being essentially in which order do you go through your data, right? Is it a fixed order? Is it random order? Where do you start from? All of this other kind of stuff, that all matters, and it's a pretty complicated relationship, how that actually ends up affecting the decision boundary that you learn. In general, there are kind of no guarantees on that side for which linear decision boundary the perceptron is going to spit out. Another good reason not to use it. Okay, let's leave classification behind and go back to regression. Okay, we're going to see how we kernelize ridge regression. So you'll recall, right, that ridge regression adds L2 regularization, right, to least squares linear regression, right? So I'm going back to W now because, I like to switch between these two. And when we only had xw minus y 2 norm squared, that was our least squares linear regression problem, right? When I add lambda times 2 norm squared of w, right, then basically what I'm doing is I'm penalizing weight vectors w, right, that have large magnitude. And then in that way, when I solve this problem, I'm hoping that I'm going to get a w with some more reasonable values, right? We motivated this from different perspectives like map estimation and things like that, having a prior on your weights w. But at the end of the day, we can also just think of it as a regularizer that we add to our objective, to our loss function, right? And when we had this particular problem, ridge regression, right, we saw that there actually very nicely is still this analytical solution. Set the gradient equal to 0 and then read off the solution. And that was given by this W star, right, which is X transpose X plus lambda I, quantity inverse X transpose Y. Okay, that was the solution that we got when we solved this ridge regression optimization problem. If this equation does not come back to you immediately, it's pretty good to review. It's something that you should be able to snap your fingers and say, oh yeah, that's the solution to ridge regression. Being that level of proficient is a pretty good idea. So at first glance, we're looking at something that doesn't look very pretty, and it might not be super obvious how to kernelize the solution that we found before. X transpose X plus lambda I, quantity inverse X transpose Y. But we're going to see how doing a little bit of math is actually going to be able to make it pretty obvious after we do the math, how to kernelize this particular solution, okay? So what we're trying to do here, right, we already know what the solution is. There's no like training algorithm or something like that. We're not doing like gradient descent or anything, right? We know what the solution is, right? We know that it's represented by this particular expression. All we need to do is turn that expression into something that can be kernelized, right? As soon as we do that, we're in business, because then we can use the kernel matrix and the kernel function in order to represent that W star and then make predictions on new data points, right? So that's what it is that we're trying to do here. So let's do a little bit of math and actually try to figure this thing out. There's a lot on this slide, but it's not particularly complicated. It's just kind of cumbersome. I'm starting from the expression that I had on the previous slide, right? And here, I'm going to label my identity matrix ID. Okay, what does that mean? It means that it's the D by D identity matrix, right? Where D is the dimensionality of my X, right? So my X, my big X, my design matrix, right, has n data points. Each of these data points has D features, right? So it's an n by D matrix, which means that X transpose X is going to be a D by D matrix, which means that when I'm adding identity to it, that should be a D by D identity matrix, okay? I can do a little bit of weird linear algebraic manipulation and write this in a more complicated way for now. Okay, what I'm going to do actually is in between X transpose and Y at the end here, I'm going to stick in an identity matrix, which doesn't change the expression, right? I can stick in identity matrices wherever I want, basically, right? Here, I'm going to stick in an identity matrix, but I'm going to write it not just as I, I'm going to write it as some expression times its inverse, okay? Because those two things together give me I, but these are the quantities that I need to pull out in order to make this manipulation happen. This is very akin, by the way, to like, if you ever see proofs and you see like, oh, like what we do is we like subtract and add the same quantity and then somehow that like lets us do what we want. It's the same idea here. I really have no idea how people keep coming up with this stuff, but I guess it's useful for us. So the quantity that I'm going to essentially multiply and divide by, that's kind of the way that we can think about it, right, is X transpose. This is not a D by D matrix, right? This is an N by N matrix, right? Because I'm doing X transpose, not X transpose X. So I can add lambda times the N by N identity matrix here, okay? And then, I can essentially just cancel it out right away with its inverse. And then add a Y here. And then basically, this second line is equal to this first line. Why? Because we only added an identity matrix, right? We wrote that identity matrix in a really funny way, right, as some big expression times its inverse, but at the end of the day, that thing is still just an identity, and we can stick identities pretty much where we want. What am I going to do now? Well, first I'm going to write out all this stuff again. And now what I'm going to do is I'm going to distribute this X transpose into this expression here. Notice that this doesn't have an inverse on it, right? So there's nothing funny going on here. This is just like a matrix multiplication, so I can distribute this X transpose into both of these terms on the inside, okay? So this is X transpose XX transpose plus lambda X transpose IN, right? And then this other thing that I had over here. Now, what is X transpose IN? Well, any matrix times the identity, you can just get rid of the identity and then, just have that matrix left over, right? So this is actually, it's just X transpose, right? But one thing that I could also do is rewrite it in another funny way, okay, where I have X transpose, XX transpose plus lambda ID X transpose, okay? This and this, these are both the same thing. They're actually just lambda X transpose, both of them, right? I'm just putting the identity matrices on different sides. And they're different sizes, right? One's D by D, one's N by N, because X transpose is not square, right? So when I switch the side of that identity, I have to make sure that all the dimensions are still making sense, okay? Why did I do all of this? The reason I did all of this is because now I have this X transpose that I could undistribute, right? So I could bring that out of both of these terms. I can rewrite this as something times X transpose on the right side, right? What is that something? Well, it's whatever is left over when I take out the X transpose on the right, right? And it turns out that this is X transpose X plus lambda ID. What am I going to do next? Cancel it out, right? This thing is the inverse of this thing, so when I multiply these two together, I just get I, right? So then I get only the stuff that's left over on that side, which is X transpose, XX transpose, plus lambda IN inverse Y. Okay, that's enough of that. I wanted to show you that because when I first learned this, somebody just told me that this thing is equal to this thing, and I spent like an hour wondering why. So I just didn't want you to do that. It's actually pretty simple. I mean, there's a lot of manipulation going on, but nothing about it is super complex, right? There's just some interesting, adding and, multiplying and essentially dividing, right, by like these terms that cancel out, which allows you to do these manipulations and then turn this thing on the top into this thing on the bottom over here, and these two are equivalent expressions, okay? That's pretty much all we're doing here. Yes? So how did I distribute this thing into this thing? Yeah? So, okay. So basically, does this first term, is that one clear? Like X transpose. So I guess maybe the way that we could write it generally is, right, if I had like X transpose like A plus B, right, assuming that all these dimensions make sense, this is just X transpose A plus X transpose B, right? It's like the basic law of distribution just applied to, higher dimensional matrices, right? So that's how I get this first term right here is that, this thing is A, right? So then I basically just get, X transpose times A, right? Here, lambda is a scalar, right? That's a single number that's multiplying IN, right? So we can think that this is like the identity, but like all of the diagonal ones are scaled up to lambda or down to lambda, basically whatever if it's bigger or larger, right? So then if I wrote X transpose lambda IN, that lambda is a scalar, so I can pull it all the way out to the front, right? And then that'll give me lambda X transpose IN. Does all of that, or is that, should I have some what? Oh, sorry, yeah, so you're asking, should I do this? Yeah, I should definitely do that. Nothing else really makes sense if I don't do that. Yeah, thank you. Yes? Why do we want it in n dimensions instead of d? Yeah, totally. So am I just doing math to bore you? Sometimes I do that, but not today. So we're going to do this because we're going to see on the next slide that it makes things easier to kernelize. That was always the point to begin with, right? We want to figure out, how do I write things only in terms of inner products between my data points? And that's what XX transpose lets us do that X transpose X does not let us do. That's kind of the key point, okay? If you don't believe what I just said, go try to figure out what is the ijth element of X transpose X and what is the ijth element of XX transpose. Those two things are quite different. Yes? Right, so we are going to see on the next slide what XX transpose is, but I claim that it's a lot simpler to work with for kernelization than X transpose X. I think I saw another question up there. No? Okay. So let's go ahead and do that. So we've rewritten our W star, right, as X transpose XX transpose plus lambda I, Y, for a n by n identity matrix rather than a d by d identity matrix, okay? So now my question is, what is XX transpose, okay? Specifically, let's think about what is the ijth element of XX transpose. So I hear X transpose X. What X? Like which X's? Yeah. So people sound a little unsure about this. It's a good exercise to go and work this out on your own if you're not sure exactly why this is true. But it is indeed the case that the ijth element of XX transpose is XI transpose XJ. Okay, that much I can tell you for sure. Why? Well, it's because in X, every row is a data point, right? And in X transpose, every column is a data point, right? So when I'm looking at the ijth entry of XX transpose, I'm multiplying, or I'm doing a dot product, right, between the ith row of X and the jth column of X transpose. Those are both data points, right? Xi, Xj, right? And then that's how I get Xi transpose Xj. This is not true, right, for X transpose X, because the ith row of X transpose is a feature dimension, not a data point, right? And similarly for the columns of X, right? And so that's not what we want to do. We needed XX transpose and not X transpose X. That was the big thing that we needed to accomplish, okay? This matrix has a name, by the way. XX transpose is oftentimes called a Gram matrix. And what's cool about this is that actually we could directly replace it with our kernel matrix K, right? What was our kernel matrix? Kij is the inner product between, phi of xi and phi of xj, right? XX transpose, the ijth element, is xi transpose xj. So if I put phi's everywhere, all I'm doing is replacing XX transpose with K, my kernel matrix. That's all that's happening, okay? And those two things have the same dimensionality. They're both n by n, right? So this is kind of checking out in the right way. We do, however, need one more thing. What is it that I'm still missing? Yes. An alpha? So actually we don't even need alphas. We're all good on that front, right? So the alphas before were more about, learning the W or the theta that I needed. Here, I actually already know what W star is, right? And I have, this XX transpose that I've taken care of, right, by just putting K in its place instead, right? But I claim that we're not quite done yet. Sorry? So lambda is going to be okay, because lambda, just some hyperparameter scalar that we pick, and then I is, the n by n identity matrix. All of that is good. Yes? Yeah, so regress, but yeah, same thing, right? So actually, we haven't talked yet about how we predict when we're given a new x, right? That was the other thing that we're looking to do, right? And there's actually a good reason why we need to specify this is because we still have this X transpose here on the outside. We never dealt with this, right? We dealt with this XX transpose. That turned into K. That's great, right? But this X transpose on the outside would still be a big issue, right? If I needed to turn that X transpose into phi of X transpose, so to speak, right, then I still have to represent those featureizations directly, and that was the thing that I'm always looking to avoid doing, right? Fortunately, there's a very simple answer to this. And the answer is that when I'm regressing on a new x, right, predicting y from x, what does my prediction look like? It just looks like W star transpose x, right? That's the linear prediction that I'm making. And this thing, right, what is W star transpose? Well, it's this whole thing transposed, right? How do I transpose this thing? I transpose every individual part of this multiplication, and then I reverse the order, right? So this thing transpose is Y transpose, and then this thing is symmetric, so when I transpose it, I get the same thing, and then X over here, right, which is X transpose transpose, right? So then when I'm making a new prediction, W star transpose X, I can use this particular expression, Y transpose XX transpose plus lambda I inverse XX, okay? I claim that we're done because what is XX? Well, XX is a vector, okay? And the ith entry inside XX, big X, little x, right, is actually another dot product. It's XI transpose X, okay? And what's good about that is that we can replace XI transpose X with the kernel function evaluated with XI and X, right? So now we've turned everything into something that has to do with either the kernel matrix or the kernel function. All right, no phi's left anywhere, right? And that's perfect because that means that we're done here, right? We have no need to represent featureizations explicitly. We've done everything now in terms of the kernel matrix and the kernel function, and that's it. That's kernel ridge regression right there. All right, I left this last slide here if we had time, and miraculously we do, which I'm actually quite surprised by. And I wanted to tell you a little bit more about this RBF kernel that I told you about last time. Remember I told you that there was something called an RBF kernel or a Gaussian kernel that essentially corresponds to an infinite dimensional featureization phi, right? One that we could never even write down no matter how hard we tried, right? No matter how much memory we have, we can never store it because it's infinite dimensional, right? So something like this, working with this particular featureization, is only possible because of kernelization, right? Otherwise, it would be, quite obviously impossible. And the RBF kernel ended up looking something like this, where my kernel function, right, k of x and x prime, was something that looked a whole lot like the PDF of a Gaussian, right, without some of the, normalizing terms. But that's why people also call this the Gaussian kernel. What is cool about this? Well, if you really wanted to, you could understand it as an infinite dimensional phi of x, and that actually is, an exercise that you'll do on a future homework, trying to figure out what the phi of x actually is. But I think that at this point, that intuition is no longer particularly useful, okay? It is nice to know that it corresponds to a really expressive featureization, but that expressive featureization is probably better understood as just measuring a distance, so to speak, between x and x prime. Why do I say that? Well, basically, the closer x is to x prime, right, the larger, right, that kernel function is going to evaluate to, right? Basically in the exact same way that, we have a Gaussian PDF. If you have x is equal to mu, that density is maximized, and as you move away from the mean, you're getting exponentially smaller, right? And this looks like Gaussians, and that's really cool because what that means is that for linear regression, right, if I use ridge regression, for example, using an RBF kernel, this prediction function, which used to be linear, is actually now a linear combination of Gaussians, and it could look something like this, right? So for example, if I had 4 data points, and I have 2 data points that are -1, and then 2 data points that are +1, right? And remember, we had, this linear combination of these different Gaussians. Now, what's really neat is that I used my linear model, right? Something that was just like W transpose X, right? I used my linear model to represent, regression functions that are way more complex than that, right? And that's kind of the high-level idea behind the power of featureization. We have simple models that we know how to solve for, but then we can combine that with really expressive features and then still get models that are really useful in the real world. That's why RBF kernels are so popular. And, I just thought it'd be kind of cool to, show this illustration. It kind of really